hurt.
Yeah.
All right, so let's start. So this is Roland Kuhn. He's a doctor. In case,
scientist.
if you have problems with some particles. So he's the Akka tech lead. Does the work on the awesome Akka runtime. And
that is Viktor, and he's technically my boss. So, and he's also a legend, but that you know.
All right, so let's get started. So we're going to talk a bit about concurrency today, and there's a lot of confusion around concurrency, especially when you mix in parallelism in this. So we're actually going to completely skip all that is parallelism and just talk about concurrency. And to do that, we need to first define what we mean when we talk about concurrency in this talk. So we have identified a couple of characteristics for concurrency that we think make a whole lot of sense when it comes to programming. And those are compartmentalization, structuring your code so that it's compartmentalized. So you have different areas or different things that are separate from each other. And then we have coordination. Does everybody see this, by the way? Coordination, so you have things that are separate and now they need to collaborate in some way, and as such you need some sort of coordination between these separate things. And, of course, it wouldn't be a complete picture if you have some sort of execution of these separate things. They would just be dormant and not do anything useful. So, having these things, we could essentially create something like a triangle and try to plot where different concurrency abstractions fit into this triangle. And that's something that we're going to do today.
But we mean basically to plot them with the weight of how much the abstraction helps you achieve that goal. It's not if it does it. I mean, you will see. You can do everything with everything. We want to focus on what it really helps you with.
So, the name of this talk is Concurrency, the Good, Bad, and the Ugly. And of course, if you have a different way of doing things, then they're going to have different good and bad and ugly things. So what we're going to do is that we're not going to do any type of plotting of how good, bad, or ugly something is. But we're going to list what we think is good, bad, and ugly about these things. So without further ado, are you ready for some concurrency abstractions and a lot of opinions?
Yes.
Awesome. All right, so first runner-up, we have threads and locks. So how many of you have used threads and locks in the past to do concurrency?
Wow. How many liked it? Okay.
So we're going to be fair. The good with threads and locks. Do you agree that it's good that they can be mapped onto CPUs so they can actually do something? Do you agree? And if at any point in this talk you strongly disagree, just wave your hand or something so I know that I have triggered some nerve. Something that's also good is that because they can be mapped onto CPUs, you get to the metal of things. It's very low overhead. You're really going as far down as you can.
That's wrong.
It's wrong?
There's a lot of overhead.
You think?
Yeah, the context switch between threads.
It depends on how many threads you have and how many cores you have and what OS scheduler does.
Because you've got a lousy schedule.
Yeah, exactly. Let's take it outside. All right, so with threads and locks, you have a high degree of control. So it gives you everything, but it's sort of in your responsibility to do what you're supposed to do. And I think you can argue that amongst the different tools of concurrency today, you do have quite good debugging. So you have stack traces. A lot of debuggers can help you do debugging when it comes to threads.
How do you reproduce executions?
That's tricky, of course. But at least you have a stack trace. You know where you're at. right? You don't have like a callback somewhere and you didn't know where it came from. So compared to other means of concurrency, I'm not saying that it's perfect. I'm saying that compared to other things, this is sort of in the good spectrum. All right, so as you can imagine, there are some bad stuff as well. So they're quite heavyweight. Like creating a thread is not something that you do on a whim. And you can't really create that many of them. So they're kind of scarce. You can't really misuse threads and think that you can have as many as possible. And it's diminishing returns. So you create 10,000 threads, you're not going to get linear scalability. So diminishing returns, you create more threads, you get actually worse throughput and performance. And this is sort of an implementation detail, but in every operating system I know, the wake-up lag for a thread is quite long. So on the JVM, it's going to be tricky. You go to sleep too often and wake up too often, you're going to get really bad performance. And the good thing was that it gave you a lot of control, but you could say a very bad thing is that you don't get much. So you have to provide much yourself with threads and locks. And how do you recover from failure? You have a thread, it blows up. Who's responsible for dealing with that? How do you know that a thread failed? How do you know what's safe to do? So it's a very hard to recover from failure when you use threads.
Jonas covered that in some depth.
Yeah, and also with deadlocks. Recovering from a deadlock is not obvious. All right, so we have a couple of uglies. Have you asked yourself this question at any point in time when you were doing threads and locks? It could keep you up at night, actually. So this is the standard thing is that, am I taking too big or too small locks? Am I taking the right locks? Am I taking the right ordering of locks? And since you don't have this means of error recovery, it means that you're going to be paranoid at every step in your thread to make sure that you're sort of trying to deal with any type of combination of problems that are going to occur. And, honest to God, do you understand the Java memory model? Because that is essentially what it forces you to do. And I think that's fairly ugly to force somebody to understand something that complex. So, let's plot threads and locks. We put it here. So, a lot of focus on execution, running things, but it's not really compartmentalizing anything. It's hard to know what's running inside a thread and what's not running inside a thread, because everything is running inside a thread. And it's not really helping you, giving you good tools to coordinate, because you don't know if you took the right locks, the right order, or if they're too big or too small. So it's not really helping you with coordination. All right, next thing.
Next thing. I think we need to speed up a bit.
Yeah, all right, talk faster. Event loops. And we're bunching executors into this. So sort of something that you attach something to run on. So, good. You can configure the execution. You could have single thread, multiple threads. You could even have like an M to N task to thread ratio where you can tune how many tasks and threads you have.
Making better use of a scarce resource.
Yeah. And you have less Java memory model headache because you don't have to worry about safe publication at the same level as you do with threads and logs. The bad things, how do you handle errors? You have callbacks. Who does what when a callback fails? How do you deal with blocking code? Like if you only have one thread of execution and somebody needs to block, how do you do that? And it's very easy to just do the normal thing where you close service immutable state in your callback. You use it because you assume that you only have one thread of control, and you know that you have exclusive execution right now. And it turns out that when you run on multiple threads, your program is completely broken. The ugly, callback hell. Creating these horrible structures of callbacks. It's very hard to reason about. Really hard to do stuff. Composing the results of callbacks is really, really hard. You fork off n number of callbacks. How do you aggregate and transform using callbacks? And it's also quite low reusability because you have this thing that essentially unit to unit doesn't really do much. And the question is your code going to be run asynchronously or synchronously? Meaning, is it going to run on one thread or multiple threads? And how do you reason about your program? It might be fine, like in Node.js, to close over some mutable state because you only have one thread of control. But do you know how many threads of control you have? And do you know how many the other author of that code thought you had? And debugging callbacks is awful. Really awful. So, where do you think it goes? We put it here. So it's geared towards execution. You have this event loop thing. Doesn't really help you that much with compartmentalization. You have your callbacks, but it's sort of like entangling things, and they're not really in the same scope. And the coordination is really tricky. How do you compose your callbacks, and how do you do stuff? So it's not really helping you with that. It's slightly better than threads and locks. So, STM. I heard that being discussed like just a second before we started the talk. So, what's good about STM? So, does everybody know what software transactional memory is? Yes. Awesome. Yeah. So, let's just go faster. So, what's good about STM is that it's type safe and non-blocking. It's also transactional, which one could perceive as good. Composable is good. You can nest transaction and your code actually composes or transactions compose. The bad things about STM is that the size of your transaction is going to impact your failure ratio at runtime because your transaction, it's easier to clash with other transactions. And it's very hard to reason about what that does to your runtime performance. Retries, so when you have contention, those things are really costly. So it can be hard to reason about how much CPU, like how is my program going to behave under contention? Because you might rerun a lot of logic a lot of times. The ugly, dealing with side effects in STM needs very careful consideration because since things are retried, you don't want to be side effecting in a retry fashion. Unless you're idempotent, for sure, but creates a very special environment. Also dealing with failure of a transaction. What do you do when a transaction cannot be committed? Where do you deal with failure in your transaction? And this unpredictable performance. It works really well when you're testing and stuff like that, but under contention it can completely fall apart. And debugging. So, as things are retried a lot of times and things fail, it's really hard to get a full picture of what's happening. So debugging is not really nice in STM. So STM goes here, because STM has nothing to do with execution at all. It's just
means it doesn't help you with it.
It doesn't help you with it. So it helps you with coordination. And it helps you with compartmentalization. So it isolates things into transactions, and it helps coordinate things inside those transactions. Java features?
I can take the Scala features.
Yeah, so Java features with the executor service. How many of you have used that? Submit, getting a feature out? Cool. So the good with Java features is that you have configurable execution. You have your executor service. You can configure how many threads it has, and you can tune performance like that. It's type safe. You submitted something, and you get something out, and it has a type. The bad thing is that the only way to compose them is by blocking. So get something out, you need to block. Get something else, you need to block, and then you need to compose it, do something else. It leads to sort of guesstimation of deadlock. So as soon as you do blocking, how many threads do you need at the very minimum to avoid deadlocks? And you have to guess. It's really hard to reason about. And also, features are sort of one-off. So you spawn a feature. When it's done, it's done. So it doesn't really give you the pump style thing or the stream type thing. The ugly things about Java futures is that you can cancel other people's futures. So you pass a future to someone else, you cancel it, or you send a future to two other guys and one of them cancels it, and that affects the other guy's ability to do something. If you want to do anything non-blocking with the Java futures, you need to do polling. And that's pretty ugly. Also, dealing with failure is non-obvious because there's no combinators to deal with failures for the Java futures. So you're pushing that responsibility over to the caller or the recipient of the future. So, where do futures go? Put it here. The executor service towards execution, and the future itself is about coordination. Pushing something over there, and when it's done, do something with it. But it doesn't really help you with compartmentalization because you're pushing the composition on the actual caller. So it's really hard to do composition with Java futures. All right, Roland.
Yep. Who has used the SIP14 Scala futures? And who does not like them? Okay, that's great. Just a poll now and again. The Scala futures have a richer interface than the Java futures, and instead of the executor service, we have something called execution context, as you know. So what's good about that? They are still type safe, like the good old Java futures. But the big difference is that you can you have transformations you can apply on them. You have monadic behavior, so that you can have non-blocking composition. Which gives you a great boon in making the system event-driven in the form that Jonas talked about in the previous talk. You don't need to block anymore. You don't waste threads. The futures in Scala are freely shareable because they are write once. They cannot be cancelled, for example, and they have a failure recovery built in. They have combinators to deal with failure when you construct the future. Now, what is bad about them? One thing which is not optimal, at least, is that it defers the failure handling to the caller, to the downstream side. You need to put the failure handling in the place where you also describe the business logic, basically. Then these combinators are all nice, and using for comprehensions and so on is all nice, but that uses a lot of closures, and closures by default can capture anything you might pull into there, and that might pull in mutable state. And then you're in big trouble, because you think I'm using futures and they are coordinating my computations, but as soon as you have mutable state or side effects in there, it's not as easy anymore. With side effects especially, we do not have a guaranteed ordering on callbacks if you just use onComplete or apply multiple transformations to the same future. You need to use special, this and then combinator. Who has used that before? And then, yeah, that's not as widely known. That's why we put it on the bad. Of course, futures are still one-off constructs. So what's ugly about them? It's not really the same callback hell, but if you can do it wrong. If you use onComplete, onSuccess, onFailure, that's basically callbacks, and then it looks the same as any callback driven program. Or if you use recover with and create nested futures, you can have similarly ugly code structures. You should instead just stick with monadic transforms and for comprehensions to avoid that. Debugging is a bit of a problem because you don't really get the full call stack of what has happened. Where did this computation come from? Where did this value come from, which I know, oh, it's wrong here, but how was it computed?
But we are actually working on that in the Typesafe console to do tracing of futures, so could help.
So where do we put this? We think it's almost a balanced proposal because the ability to write down your code in a nice flow in one place gives you a bit compartmentalization. It's not yet perfect. We will see how that can be improved. You still have execution context giving you the configurable execution, and it still coordinates. If you don't do dumb things, then it still works as described. So this is approaching the middle of the triangle. You want to? Yeah, go ahead. So that's a bit older. We had a Dataflow module which was inspired by Oz Dataflow.
Have you used Dataflow?
Yeah.
Know what it is?
Used it. So that's basically it's basically the same. It's the same features, and it just has some sugar on top, so that you can write down your code in a direct style. So it's still type safe and non-blocking composition because it's just normal features under the hood, but it's declarative. You just write down your code as you like it. You're not forced to use a for comprehension even. You write x equals y plus 5, and if y is a future, and x will be also a future. So that gives you the ability to write down your logic even closer to how you wanted, what you wanted to express in the first place. Less gymnastics needed. And if you do it without side effects, then Dataflow concurrency is completely deterministic. No matter how or where you run it, you will always get the same result for the same inputs. Scheduling when to compute what does not have any influence, because the dependencies between the different computations are expressed naturally in your code and are observed by the runtime. The Akka Dataflow is based on the CPS plugin. That's the compiler plugin for the Scala compiler, which does a continuation passing style transformation of your code. And this plugin is able to do that transformation even across method calls. So you can have this kind of composition even in a non-local fashion. Now, what's bad about this? This CPS plugin introduces some very special types.
How many of you have seen the CPS error messages? How many of you would say that they are easy to understand?
So they can be quite confusing, and not immediately point out that you can't use them in a for loop, for example. You can't put something in there. And the error which you get does not tell you that. It tells you something completely different. That's not obvious. Well, of course, Jonas also said it. That it's not a silver bullet. It has limited applicability to deterministic data flows. That's what it's made for. Error handling means that you need to step outside of this model. The nice way of writing down the combinators, so to speak, in a direct fashion, work only for the blue sky scenario. And yeah, debugging is bad as for most other things. And it's still only futures. What's ugly is basically only the CPS plugin error messages. So here we think we can put that square in the middle of this triangle, because it helps you express how you want to execute it and how things shall be coordinated and how things shall be compartmentalized, because you can use all the normal tools in your toolkit, programming toolkit.
And also you don't introduce new namespaces or scopes for your transformational flow, which means that all your code is sort of in the same compartment, the code organization. That's why we put it higher on the compartmentalization.
Shall I quickly do Scala Async?
Yeah, you don't need to do it quickly. I think we're pretty good on time.
Oh, okay.
We're talking fast.
We're talking too fast. We need to talk slower. So Scala Async is very similar to Dataflow. It's basically the same idea, just implemented in a different fashion. So it's still type safe. It's operating still on futures by default. And it's extensible. You can do other things with it. Non-blocking composition as usual. It's the same kind of direct way of writing it down as in Dataflow. But the difference to Akka Dataflow is that it's local only. The transformation which is applied cannot span method calls. It's a local thing. But that, on the other hand, I should probably stay on this slide. That's a good thing we didn't write down. It's more efficient memory allocation-wise, because the CPS transformation means that every time you have a continuation, you allocate a new closure, expressing what to do whenever that new result comes in. And the async implementation sidesteps this issue by implementing this transformed method body just in one object. And it's just a state machine in there. No allocations necessary, but beyond the first one. But the bad thing is still limited applicability, the same as for Dataflow and debugging, and as usual for futures. And what is really the least nice thing about it is that still error handling forces you to step outside of it a bit. And the nice way of doing things only works for the blue skies. So all in all, it gives you the same benefits with a slightly different trade-off. Yeah, it's local only, less allocations, and no CPS plugin error messages. So do you want to talk about threads and queues?
Yeah, we put it at the same as.
Oh, I looked at the wrong screen, sorry. Yeah. We put it in the middle.
All right, so far, which one is the favorite? Threads and locks, or the event loop, or futures in all different combinations? Scala futures, how many of you think that Scala futures? So far, Scala futures? Yeah, that's pretty good.
Java futures?
Wrong crowd. Event loops. How many of you think that event loops are easier to reason about?
No JS.
No, nothing.
Sorry.
All right, so looks like we have some type of gravity towards Scala futures so far. So threads and queues is the next thing. So how many of you have somewhere or somehow decided to put a queue between threads to do thread-based programming? That's a lot of people, actually. Okay. So how did you find that? We'll see if you can agree with these good, bad, and uglies. I expect hands waving in case you disagree. All right. What's good is that this queue that you put in between the threads is type-safe. You can define whatever type that queue to have. And you get to make the choice. Do you want to do it in a blocking or non-blocking fashion? Do you wait for something to be available, or do you just pull it sort of occasionally? Since you have this queue, you essentially decide if you want to do back pressure or not. So that's a good thing. So what's bad about it? Well, I think it's still quite heavyweight, because you still have that thread you have to allocate, and you still have that queue that you need to put in between. And I mean, still, we're still using threads, so they're still scarce, and we still get diminishing returns, and we still have a high wake-up latency. We haven't really raised the abstraction here. We've just, instead of having the locks, we just replaced them with a queue. So it's not high level. You could say that it's not low level, but it's definitely not high level. And we still have no means of recovery. We haven't added that. So the ugly stuff is that how do you propagate your failures? Still, what you have an in queue. Where do you put your errors? And since queues are sort of unidirectional, you're communicating one way. You're communicating to some other queue. And to be able to respond there, you need to know his queue, or he needs to know your queue. So, to conclude, we still back at threads. We replace the locks. We're there. So we've added some coordination using this queue. And we've added some compartmentalization, because we don't have to put these locks everywhere. But we haven't really gained much from normal threads and locks. So, you ready for some more? Do you agree with this conclusion, by the way? Or do you have something else that's bad, ugly, or good.
They're really easy to reason about.
They're really easy to reason about. That's a good thing. Yeah, absolutely. So, yeah. So the downside is when you do bidirectional queues, or if you don't have a directed flow of things, it's easy to get into deadlock situations where you're communicating back.
Yeah, how is that different from a simple actor model?
So in this case, you have a queue, you're putting something into a queue, but how do you send around a queue? You'll have to sort of like, okay, you're communicating with a queue, so sending around a queue everywhere, and you don't necessarily know, is the guy that consumes from that queue, is he alive or dead, or... Yeah, it's sort of, yeah.
It is a very simplistic actor model. But the kind of actors we are going to talk about next, which we implemented in Akka, are much more complete. Because they give you an abstraction for the queue, and they give you failure management. I'm getting ahead of myself.
He loves actors, that guy.
I'm sorry.
Crazy. Who'd have known? Who'd have known? All right, so let's talk about some fun stuff. So, actors. How many of you know what actors are? That's so good.
Great.
4 years ago, that was way harder. So, let's be honest. Let's be honest. What's good about actors? So, we have encapsulation. So, an actor is sort of standalone. You can't really peek into that actor and do stuff. You have supervision to deal with failure. So you can observe failure and you can restart actors. You have the configurable execution that you have with the executor and executor service. And the good thing here is that a lot of these other things were purely local. So threads and locks is really, really difficult to do in a distributed setup. Like a distributed JavaUtil concurrent lock doesn't really exist in the JDK, and normally the concurrency abstraction tend to be very local centric. So a good thing about actors is that it tries to make the local thing an optimization. I think the good thing about actors is it tries to sort of model the real world. It has sort of, you send messages and you respond to messages. It's more like how you do communication in the real world. It's instead of like writing to memory locations, so sending and receiving messages, or more real world model. And as a model in itself, it requires less guarantees than the other models. So when you call a method, you're expecting it to be once and only once, and you will call that method, you will execute that logic, and once it returns, something has been done. So it has a very high guarantee set, and actors can actually relax that a bit. So we think that's a good thing, because you shouldn't be paying for things that you don't need or use. So what's bad about actors? So I think a lot of people agree that untypedness of actors is a bad thing. So an actor essentially receives any type of message, and it can be hard. It's not type-safe in that sense. So the unitypedness of actors could be considered a bad thing. Somebody might think that explicitly managing the life cycle of an actor is a bad thing. I tend to agree, because what we're talking about here is how it helps you as a programmer, and explicitly managing life cycle can be a tricky thing to get right.
It can also be a very necessary and good thing. But if we're talking about mass adoption, then I think we need to chalk it up on the bad side.
And I think debugging is still worse than, for instance, for threads, etc. It's also something that we're working on solving by having tracing. So sort of like a distributed stack trace when it comes to actors. What's ugly about actors?
Yep, they're ugly.
What's ugly about actors? Well, it's easy to violate your encapsulation by exposing your inner self to others. And that's sort of a function of having these greedy closures, etc. Composition can be awkward since they are untyped or unityped. composition doesn't feel like type-safe function composition in that sense. And where do we put actors on this thing? Well, we think that it actually has better compartmentalization than the other things that we've seen, because it really tries to avoid people peering into that thing. You only have the reference to the actor, and that thing can live anywhere. And it still helps you with coordination and execution. But it's mainly focusing on the compartmentalization. All right.
Yeah.
You want to do RX?
Yeah, I'm doing the risky stuff. So our knowledge up to now was quite well-founded, and for the next two topics, we've just begun researching. So if you find errors in these slides, wave and raise your hands, right? So
I will take it outside.
Reactive extensions came from .NET, but there is also are multiple implementations on the JVM. So we thought we might look into it and try to discuss what's good and bad about it.
How many of you know what reactive extensions are?
So in a nutshell, you can think of it as a data flow, but it's not one-off, it's reusable. It's about data flow for streams. You compose it in the same way as you compose futures, basically, but it's not just one value which gets put in, it's a stream passing through, and you're describing the transformation of the stream. That's, I think, the essence of it. And this is all, it's basically an implementation, a specific implementation of the observer pattern. As such, it is type-safe. It allows you non-blocking composition. You set up your processing graph, and then you let the data flow through it. You have reusable components which you can plug together. That's pretty good. And it's stream-centric, which can be exactly what you want. I mean, the canonical example is GUI programming, where you see the mouse position as a stream of points, and you transform that and then combine it with the click information, and yeah. What's bad about it? Still, in contrast to actors, which really reify error, failure, and escalate it, in the streams, you either have the errors flow in the stream, so you defer it downstream, or you still have it in stream, but when you construct your flow, you put in stages which explicitly deal with errors. So it's still entangled, the business logic and the error recovery. Also, you need to explicitly manage the lifecycle. If you do not want to observe anymore, you need to deregister. Like you need to stop actors. It's basically the same thing. And there can be glitches. So events propagating through this graph can reach a certain component down here, mostly in the order A, B. And then you program for it, and it goes, everything works. But sometime in production, it goes B, A, and then it breaks. That's basically what a glitch is. And debugging, I mean, it's callbacks. It's the observer pattern, so debugging is as hard as it always is for these paradigms. What is ugly about it? Basically that it's callback. It's not callback hell, because it's raising the abstraction a bit. He thought it should be callback limbo.
It's close to hell, at least.
And what is inherent in the observer pattern is that it inverts your control flow. You always work yourself upstream in the way you write your code. You do not write the code in do X, then do Y, then do Z. You write your code, and if I want to do Z, so I register for Y, basically. So where do we put this? We think it's actually pretty well balanced, and as it is basically data flow just reusable, we put it in the same spot as data flow. And the last one, which we know least about, I must say.
Do we have an expert? Functional reactive programming expert?
Do we have experts here who can react?
Don't be shy.
Yeah, if we make mistakes. So, functional reactive. That's basically, if you take Rx, I don't know whether it's implemented like that. If you would take Rx and you put observable points along the way, which just give you the current value, so you can sample the current value at different points, then you work with these values, basically. It's not stream-centric, it's value-centric. It's still type-safe, and it's declarative value composition. So you write down, like in a data flow as well, that x depends on y plus 5 or something. And then the right things happen. So it is direct style. It's the natural form of flow. It's not inverted control flow as for Rx. And if you don't do side effects, as always, it's completely deterministic. So this means for FRP there are no glitches. But in order to achieve this, its execution must be single-threaded, basically. It constructs a graph of your dependencies of all the values you deal with, and it needs to keep this graph in a certain topological order, and it's basically clocked execution so that you can exclude glitches from happening. And that means it's single-threaded.
On a per stream basis, right? Like each stream has to be single-threaded with multiple streams.
It's like partitioning. If you really have separate things, then of course they can be run. They're still separate. They're still single-threaded in each stream. So.
Yeah. And the ugly thing is, of course, if you do side effects, then you can reintroduce glitches. Then you can make them visible. Unless I read that paper wrong. Correct me if that's a mistake.
He's very silent, so I think we're onto something here.
Yeah, might be. So where do we put this? Well, basically, since it's single-threaded, we put it as far away from execution as possible, because it doesn't really help you with writing a scalable solution, for example. But it gives you coordination and compartmentalization.
All right, so we're pretty good on time here. Man,
Yeah,
getting good at this stuff.
you're a manager. You managed it.
All right, so are you guys ready for a summary?
Yeah.
Yeah? You're all good? Blood sugar is high? Awesome. All right, let's do it. So we have this triangle that you've been looking at for quite a few times. So let's plot these things out. First, we have the STM. Then we have the Scala futures, FRP, Java futures, actors, Dataflow Async and Rx, which is sort of like very similar but makes different trade-offs, and thread plus queues, executors, and thread plus locks. Does this make sense? Do you agree with this picture? Because you have to speak now, or
keep your silence.
One comment on async. So I just wanted to point out that async actually doesn't take anything away from Scala feature. It just adds convenience, right? So many of the issues are the same, right? So and the other thing I wanted to point out is something I forgot. So
Yeah, you will remember.
all right, so it comes directly from the author himself, so let's just agree that he's probably right there.
Yeah. So this is not supposed to be a ranking in any form. Yeah?
No.
It's not that higher up is better. I mean, we could have turned that triangle around. It's just that compartmentalization is such a long word. It fits better.
Completely imbalanced.
So,
I remembered my point. Sorry.
Yeah.
The point was, this was already mentioned, that async compared to CPS can be more efficient because fewer closures are created because you have an efficient state machine inside. But what's interesting is that if you write programs, this actually applies also in comparison to Scala futures, because if you use Scala futures and decoming it, just like map, color width, and so on, you also you create many closures. So with async, you can actually also, compared to Scala future, reduce some of that overhead. So
Yeah. So what's good about Scala Async is that it has a higher chance of being efficient, and it's quite nice to write as well. So I think it strikes a good balance. All right, so
yeah, but no silver bullets.
there's no silver bullets, and you need to sort of pick because you always make trade-offs. So I'm not saying that anything is better than the other, but from a personal perspective, really try to stay away from like the lower right corner. All right, so to conclude this talk, where we've sort of just blurted out opinions, and I think what you should do is that you have to pick your poison. Thank you.